Thank you so much for this great introduction and this great opportunity to talk in this very esteemed plenary session of the Pontifical Academy of Sciences. It's a great honor even for me to be part of this program, seeing our great role models here. So today I'll be talking more on TB-associated lung inflammation as a target for therapy development. And of course, at the end, I'll also talk about potential implications on COVID-19 severity and probably how actually TB problem or COVID has actually made us reshape our efforts towards managing TB. So as they mentioned, I'm actually from Africa Health Research Institute, an associate professor at UCL, but I'm largely based in South Africa in Durban, where we also link to rural medicine doing TB there. So TB doesn't need introduction. From recent report from World Health Organization, we still having TB as a leading, of course, this is before COVID-19, but TB remains the leading infectious disease from single bacterial infection, with over 1.5 million people dying from TB. And of course, this problem is enhanced more, is aggravated by populations that are still immunocompromised due to HIV infection, for instance, where there's no treatment. And of course, there's emergence of drug-resistant strains. So there's a need in order for us to address the millennial developmental goals, which include eradicating TB by 2030, we really need better strategies to develop more sensitive diagnostics earlier, and also better therapies to augment current treatment strategies against TB. So TB exists as a spectrum. Traditionally, we always thought of TB as an active disease and as well as latent form. And we largely diagnose TB at the active form of the disease because of the positive spectrum, positive sputum that has the bacteria in it. And this is where basically people start treatment. But before that onset of the disease, there's a lot of events that suggest already that one is at the risk of converting to active TB from latent TB. For instance, there's a stage called subclinical TB here, where we already know that as early as 200 days before people are actually diagnosed by TB, there's already some factors happening in the lung that actually shows that there's inflammatory risk that could eventually lead to damage in the lung and then actually for the bacteria to spread. So basically there's a need to diagnose there's a need to develop biomarkers that can tell us that one is at the risk of getting TB in the near future, that perhaps can actually be treated quickly to avoid actually the active TB disease. My thought is that by the time we treat people, there's already so much damage in the lung and the bacteria are all over the lung such that the treatment would take long as it does at the moment. So if we treat early, potentially treating the inflammation that's associated with the damage in the lung and also target the bacteria, we could quicken or shorten the course for therapy and actually avoid serious damage in the lung. So basically that's my area, our area of interest in where we work actually. So our bigger interest to intercept the TB transmission across the spectrum from the beginning all the way to the end. But I'm going to be talking about the basic component of basic science, which is more at discovery by looking at basic research and what are the disease determinants that we, in that case, we actually identify molecular drivers of TB progression in the lung and to see whether that translates into blood. And then we evaluate those promoters of pathological lung damage as targets for host-directed therapies. And of course, later on, the goals is to develop new tools and early phase trials based on host-directed therapies and biomarkers that we can use for testing preclinical models, as well as early phase trials in patients. So as I mentioned, so I'm interested in pathology. So in 1882, when Robert Koch crushed the tubercle or the granuloma, what he did, he actually crushed something that was a structure of the lung. And we didn't know whether TB was actually a disease that came from bacteria, but we know that as early as 400 BC, a lot of Greek philosophers, Hippocrates as well as Aristotle, they were already actually inferring something that's similar to modern TB. In fact, but then it took over 2,000 years for us to know that there's a bacteria behind the disease called TB. But the granuloma or the tubercle in the lung has been known for a long time. What was not known was that there's a causative agent, which is the bacteria that Robert Koch discovered when he crushed these tubercles in 1882. And of course, from there, the efforts are being to develop therapies that are meant to kill the bacteria in the lung, but we forget that manifestation of the disease also comes secondarily because of the damage that's happening in the lung. So my advocacy here is that while we treat the bacteria, we also need to treat or avoid damage in the lung. So this is about combinatorial therapy, which is host-directed therapies. But a granuloma is formed when bacteria are inhaled in the lung. They go in the alveolar spaces in the lung, where actually they're captured by immune cells, such as cells called macrophages, and as well as some neutrophils in there, but largely there's actually also T cells, like B cells and T cells, that would actually come and form an organized structure called a granuloma that is containing the bacteria at the center with arrangements of various cells here. I'm not going to go into detail on the granuloma structure per se, but it represents this solid containment of the pathogen, which we believe is a good thing that many people who are exposed to the bacteria or infected with the bacteria, but do not develop active disease in their lifetime. We believe it's largely because of intact immune system characterized by this intact structure containing bacteria at the center. So in that way, we look at a granuloma as a good thing to contain the bacteria, such that there's no transmission of the disease. However, granuloma things can go wrong, that the granuloma that is very good and containing bacteria can move from a solid form, like this is a solid granuloma, that can cause things called caseation or acacium, which is like as in German or Afrikaans, like gas is cheese. So it's a cheese-like structure that many people would see in the lung here when they look in the lungs. And this is the beginning of the damage of a granuloma that was very attractive, and it forms this calcium. And a calcium can fall off to lead to cavitation or formation of cavities in the lung. So when you think of a spectrum from a healthy lung where bacteria was contained by solid granuloma that caseated and led to cavity formation, and within these cavities, it's exactly where we had bacteria contained nicely. So this is where the bacteria that was contained now can be coughed out and can be transmitted and spread out through the lung. So our interest again is to move from here at a very good granuloma to a granuloma that is cavitated, to see what happens that drives this pathological spectrum, and whether we can identify factors that promote this damaged progression, and whether those factors present biomarker opportunity, or whether those factors, if they promote the disease, can be intercepted to develop therapies. So what we do, our approach, or maybe what we did previously also, was to use laser capture microdissection, which dissects unique regions within different forms of granuloma. We use lung species from patients or TB patients who had undergone surgery like pneumonectomy, lobectomy because of severe lung damage. So we use those tissues, and then we use laser capture microdissection at all different regions, and then we solubilize these things, and then we take them into mass spec, for instance, and then we identify all proteins like proteomics associated with different stages of the disease, with the aim of identifying inflammatory markers that will give us a clue the difference between these regions. And obviously in proteomics, for instance, one would get thousands of differentially expressed genes, in this case proteins, different abundance of proteins depending on the region, and also mirroring the spectrum of the disease at granuloma level. Here I want to give you, I'll try and make this simple. So I want to pick one pathway, for instance, that came out interesting from our study when we're identifying markers, for instance, of the disease. And one of those is a well-known pathway called arachidonic acid pathway, which is more like a lipid arachidonic acid, and it's utilized by two sets of enzymes. There's enzymes called lipoxygenases and enzymes called cyclooxygenases. But here what we found is that enzymes such as this enzyme here in blue called ALOX5, and as well as LTA4H, these enzymes, were very high in this arachidonic acid, were very high here on this heat map. They are associated with calciums and cavities, whereas normal cellular regions in the granuloma that are like solid granulomas were more lower in blue. So what we think is these high proteins that are in the arachidonic acid are actually associated with inflammatory regions and pathological damage in the lung. Of course, these are predictions from proteomics. So to validate those, for instance, we picked this protein LTA4H, and we used antibodies, immunological antibodies that would give us the spatial abundance on a tissue. So this is a tissue with a caesium here at the center and with the cellular regions. So in green, we're looking at the protein here. In green here, you see that this LTA4H is very high in this caseous regions, particularly in the areas that are bordering the caesium, whereas it's generally low on the where you see in blue is actually generally low in cellular regions. So this validates that factors that we saw that are associated with inflammation, you can also validate those in tissue by immunostaining. And of course, because TB is a spectrum and also it's a very heterogeneous disease, that within a given lung, so this in red here is a lung from one person, for instance, but you can see there's various granuloma lesions. There's actually this lesion here, and then there's also a different lesion there. But when you stain for these two, ALOX5 as well as LTA4H, consistently we see that they are in green. You can see that this molecule here, LTA4H, is very high in the areas that are bordering the caesium here. And as well in a different nascent granuloma, you can see it's actually staining nicely around. And also in a cavitary granuloma in a lung that is really messed up, you can see between cellular region and in a necrotic caseous region, you actually see too much damage there or too much expression. And for LOX5 too. So this really validates what we see in proteomics and also association of these proteins along with pathological damage in the lung. And of course, as I mentioned, inflammation is being the key interest here. So to validate whether these proteins, for instance, LTA4H, as I showed you, that they really are associated with inflammation, we used an inflammatory cytokine that's well known called tumor necrosis factor. The idea was to see whether we can localize the expression of this LTA4H with this cytokine that's a marker of inflammation. And as you can see between these two images, the one in green here, you can see LTA4H is expressed along the edges of the cavity here, cavitary granuloma. And TNF also, there's not as much as LTA4H, but it's also highly expressed in similar regions as LTA4H, indicating this association between these proteins that we mentioned with inflammatory markers. And of course, these proteins metabolize substrates. In this case, as I mentioned, they metabolize arachidonic acid here. And then we wanted to see whether we can use mass spec imaging to image metabolites now that are corresponding to those proteins that are utilizing them. And you're looking at this lung here, when we image in red, that's where you have the highest amount. So when you image lipids that are utilized by those enzymes, the LOXes, which are utilized by those enzymes, you see that actually there's high intensity of those lipids also in the areas that are actually bordering where there's too much damage. So this makes us think that those areas that are bordering caseation, for instance, are the battleground of inflammation. And this is where the expansion of the damage is occurring. And depending what happens there, that would what lead to the outcome of the disease. But in this case, we think these molecules are promoting disease progression. And of course, so looking at arachidonic acid, I earlier mentioned that it's utilized by two sets of enzymes. So there's other ones on the left is COX1 and 2, whereas on the right is the enzymes that I've been showing you, LOX5 and LTA4H downstream. So we wanted to see whether the two potential arms of arachidonic acid enzymes can actually have different staining. So in other words, because I've already showed you that on the right here, ALOX5 pathway is largely associated with inflammation. We wanted to see the one that is actually on the left, which is usually known to counter the one on the right, whether we can see.
I think we've lost you briefly.
I guess we lost the connection, huh?
Yes.
I hope he comes back.
Okay. Does anyone have a comment or question at this stage?
Oh, hi, sorry. I think I lost at some point. Hello, can you hear me?
Okay, you're okay now, yes. Yep.
Yes, I'm not sure if where I stopped, but I just realized that.
No, we're only less than 1 minute ago, so.
Oh, really? Okay.
Okay.
Okay, so I'll just try and. Okay, so yeah, so in that case, I can just I don't know, I can just finish off
Go
then.
on. Yep. Mhm.
Okay, yeah, so we actually showed that this segregation between anti-inflammatory and inflammatory mediators on the lung. So if you can see on the right, in red here, that's where you see a lot of those inflammatory proteins that are associated with the damage. Whereas in red, in the coccyx, on this layer where there's so much damage, the amount is not much, that red, but it's here on the cellular regions. So this suggests that actually anti-inflammatory mediators might be sequestering inflammation in the lung and might be blocking the damage. So it's an area for interceptions for future. And then, of course, I was going to show you how we can actually look at this in the blood. And we actually see here that when you look at the two pathways, the coccyx don't change when you look between healthy and TB people in the blood. But when you look at expression of the genes that I showed you that are associated with inflammation, they are high in TB patients compared to when you actually look at healthy and latent TB infection. So this suggests those pathways that are associated with inflammation in the lung are actually potential biomarkers for disease severity. And also for future work, we're actually looking at intercepting them to develop host-directed therapies, a host-directed therapy that's meant to limit inflammation and reduce lung damage while we are actually using first-line drugs. We believe that we can augment and improve current treatment protocol that would shorten therapy. So this here, I was going to tell you how actually like using pharmaceutical inhibitors of these molecules reduces cell death in macrophages and reduces inflammatory cytokines and potentially bacteria. But I'll finish there, and then for COVID-19, as we know that we learned a lot, but we realized that there's also positive lessons that rapid response always yield desirable outcomes because of how actually the world responded to this and in a collaborative manner. We know that with future outbreaks like this, we'll actually stand prepared to know what are the best efforts to put in place. And of course, awareness is very important in this regard. And also looking at sub-Saharan Africa, where we have like severity of TB as a disease and HIV as well. So it would be really important at the moment, luckily, I don't think HIV and TB compared to hypertension and diabetes having been the biggest comorbidities in terms of severity of COVID-19. But there's a lot of work that needs to be done, even at mechanistic level and management of these diseases to know and to learn from COVID-19. And I appreciate the opportunity. So these are my lab members in the group where we're working, and as well as funders, we are funded largely by Bill and Melinda Gates Foundation and Wellcome Trust. And I really thank you for the opportunity to talk here.
Thank you very much. And I'm sorry, I didn't realize that you were mainly based in South Africa, not in London now.
Well, UCL is my main employer, so I think they'll be happy to hear that.
Okay.
I'm in London.
Nice.